All right, here's a reaction that we've seen many times before. We've got lead nitrate and potassium iodide. And we're going to start chapter 16 with an old friend. So you might remember that this is a reaction that we did first way back in chapter 13 in chemistry, where we know that these two ionic compounds, potassium iodide and lead 2 nitrate, are going to react in a double displacement reaction, and that one of the products is going to be lead iodide, which is a precipitate. This bright yellow stuff. So this is a reaction we've seen many times before. The camera doesn't do that color justice. It's not nearly as bright as it appears in real life, so I'll try to take a still picture of this so you know what I'm talking about. So the cameras are not really doing it justice, but this is what we're looking for. And remember that if you want to get an A on the final, let me remind you there's a fast way to do it. I'll take one of these. Anyway, all kidding aside, I couldn't get the camera to take a good picture. So this is the color that we're looking for, and you can also see it in this beautiful 1982 Ferrari 308 GTSI, but we're not worried about that. Welcome to chapter 16, something called solubility product, otherwise known as KSP. And in previous explorations with this yellow stuff, this is called potassium iodide. I'm sorry, lead 2 iodide. It looks like that. And in our solubility guidelines table from way back, we would say that this is what we call a precipitate because it falls out of solution. Well, you're probably going to figure out that that's actually not what happens. What happens when we have lead iodide in solution is that it actually is aqueous and that it does dissociate into these two ions. It just doesn't do it very well. And in fact, we might say that it stays in its precipitate form way better than it stays in its dissociated form. That means that we could write an equilibrium expression, what we'll call the K for solubility, and we're going to call this solubility product, the constant for solubility product. And for our purposes, we'll treat this lead iodide as a solid. So it's not going to appear in any expression that we write. So the KSP for this reaction then would look like this. Put a little minus there. Notice that we have a coefficient of 2, and so that gives us a exponent of 2. And just like acids that have a dissociation constant, a Ka, dissociation of weak or strong acids, that indicates how well they dissociate, precipitates have a KSP that indicates how well they dissociate. And here's a table that shows you kind of what we're talking about. Let's scroll up a bit here. Wow, that's a bunch. And here's our buddy, lead iodide, right here. And it says it has a KSP of 6.5 times 10 to the negative 9. Now, these can vary widely, so we're not going to stand too much on ceremony here. We'll usually take what's given us. I'm not going to make you look these up because they tend to be pretty variable. Let's say that this is, for this KSP, we'll say it's 6.5 times 10 to the negative 9th. Okay, so what are we going to do with this? What does this mean? Let's scroll down a bit here. Actually, let me get rid of this. I'll get this out of here. Where'd my cursor go? Okay, let's get rid of this thing. Okay, so here's what this means. It means that when these two ions are in solution, because we're not worried about the reactant, just the products, they produce a precipitate that is 6.5 times 10 to the negative ninth. That's the ratio of product to reactant. So 6.5 times 10 to the negative times 10 to the negative ninth to 1. So if we wanted to solve for this, this is pretty straightforward. When this dissociates, whatever this is, whatever our rate is, that's going to be x, and that's going to be 2x. So this is pretty straightforward. If a question asks you, what is the solubility? What they mean is, what's the concentration when it reaches KSP? So let's solve for this and find out what these concentrations are going to be. And this is pretty straightforward, times 10 to the negative ninth. So we're going to call this, let's make sure we get that there. This is now 4x cubed, right? Because when we express this out, this is now 4x squared times x is 4x cubed equals 6.5 times 10 to the negative ninth. If we solve for x, I'm going to bust out my fancy calculator here. What this tells us, 6.5 times 10 to the negative ninth, remember these vary wildly, times 10 to the negative ninth, we're going to divide this by 4. And then we're going to take the cubed root. And so here's my math function. Let's take the cubed root of this answer. So we'll say shift answer. This is the concentration. We'll just call it 0.001176, we'll say. And so this is the concentration of whatever ion is stoichiometrically 1. So when they say, what's the solubility? This is the solubility. If you want to express that in scientific notation, 1.2 times 10 to the negative 3. And that means that when lead iodide reaches equilibrium, the concentration of whatever ion is stoichiometrically 1, that's lead, is 1.2 times 10 to the negative third. And you could also find the concentration of iodine because it's going to be 2x. And so what would we say the solubility is for lead? 1.2 times 10 to the negative third. And for iodine, it would be exactly twice that, 2.4 times 10 to the negative third. Now, just to verify that these work, you can plug them back in. I'm going to use the magic of technology to prove that this works. So when I plug these back in, I get 6.9 times 10 to the negative 9, which is cool because I did some rounding. I took some liberties with the rounding. So this is what they mean by solubility. What's the molarity when it reaches equilibrium? Here it is. You're solving for x, just like we've been doing, okay? So I'd like you to take 3 problems for a spin. Everybody stay safe in all this snowy weather.